Hi, I'm Scott Knockleby. In this video, we're going to look at an example of the inverse displacement solution for a spatial manipulator. So by the end of this video, you should be able to solve inverse displacement problems for spatial manipulators. So in this video, we're going to look at the example of a main arm, which is comprised of 3 joints. So it's a revolute joint, perpendicular prismatic joint, perpendicular revolute joint. So here we have joint 1 revolute, joint 2 prismatic, so this translates in and out. And we have joint 3 revolute. All right, it's connected to a spherical wrist here. So we'll make a note. This is our spherical wrist. But in this example, we're just going to say, given this wrist center position, what are joints 1, 2, and 3's values? Okay. In a subsequent video, we'll look at an example where we consider also the wrist in terms of solving. But for now, we're just going to solve the main arm joints. All right, here we have our D&H table. Okay, and these are modified D&H parameters based on our zero displacement drawing here. So each row corresponds to one link transformation. So you take the parameters, your 4 D&H parameters, stick them in your link transformation equation as we previously showed, and you get your homogeneous transforms. So we do that for each row of our table, and we end up with 4 homogeneous transforms for this main arm. Now, in order to solve the inverse displacement problem, we need the forward displacement solution. All right, and so the forward displacement describing the position and orientation of the wrist center with respect to the base frame, it's just simply those 4 transformations multiplied out together, and you get this here. So in this example, again, we're just looking at the main arm. So we're going to say, given the position of our wrist center with respect to our base frame, which would be px, py, and pz, what are our 3 joint variables? So what are theta 1, d2, and theta 3? Well, those variables correspond to the position of our wrist center, which corresponds to this 4th column of our homogeneous transform here. So we're going to be using the 4th column here in our inverse displacement solution. So we can note that our position px, py, pz with respect to the base frame is going to have to equal S1 C3 plus D2 minus C1 C3 plus D2 minus S3G and 1. Again, this is with respect to our base frame. All right, so we have 3 equations. All right, we know the left-hand side. We have 3 unknowns here. We have theta 1, we have d2, and we have theta 3. So we need to solve these 3 equations for those 3 unknowns. So let's see how we can do that. So one thing we can try and do is we want to try and isolate one of the variables over to the left-hand side here. And because we're in frame 0 here, if we multiply both sides by the transforms describing frame 0 with respect to frame 1, that in essence will isolate the theta 1 variable to the left-hand side. So let's make a note of that. We're going to isolate the first variable, which is theta 1. By multiplying both sides of equation 1 here. So let's call this equation 1. All right, so we're going to multiply both sides of equation 1 by T10. All right, we know T01, so we need to take the inverse of this to find T10. Okay, and if you do that, so this is going to be T01 inverse. So if you take the inverse of that matrix, you'll get the following. So now we're going to multiply this matrix here on both sides of this equation 1 here. And if you do that, you'll get the following. All right, that's our left-hand side. And here we have our right-hand side. Okay, and you can see we've now isolated theta 1 to the left, right? On the right, now we're just left with theta 3 and d2. So right away, we can see we have a single equation here in terms of just the one variable, theta 1. So we can solve that equation. All right, and now I'm going to do a little on the side here. So here are 5 sort of useful inverse displacement formulas. This is adapted from Appendix C in Craig. Okay. Note that Craig actually has an error in terms of these first two. This is the correct formulation. So keep that in mind. So we have this formulation here, equation 3. So we have A cosine theta plus B sine theta equal to 0. Right? That's the same formulation here. So we can use this solution here, and you'll see there's actually 2 solutions for that angle, all right, defined by these 2 equations here. So we're going to use this here to solve for our first joint, theta 1. So let's do that on this slide here. So this is from element 1,4 of our homogeneous transform there. So that's that equation 1 of, or sorry, the first equation of equation 1 there. All right, and we can show that theta 1 is simply going to be a tan 2 px minus py, or a tan 2 is minus px py. All right, so there's 2 possible solutions for theta 1. All right, so 2 solutions exist for theta 1. And again, this came from this formulation here. Okay, that's what we were using. Now, there is a special case, and we should note it. So note, if px equals py equals 0, all right, in other words, the wrist center intersects axes of joint 1. So let's go look at our drawing of that. All right, so if px equals py equals 0, that means our wrist center has to be in line with Z1. All right, so it's going to be folded back, and our wrist is intersecting joint 1. So what that means then is joint 1, there's an infinity of possible solutions, all right? Because as we spin joint 1, that wrist center won't move, okay? It will just, it's intersecting that axis, it will just spin, the arm will spin around, but that joint center won't move. So if that's the case, all right, let's make a note then. There's an order of infinity. So this means order of infinity. So we'll use that as a shorthand for that, of solutions for theta 1. So that, in that special case, when px equals py equals 0, all right, theta 1 is chosen arbitrarily. We can set it to whatever value we want. And often you would just set it to what theta 1 was in the previous instance. Okay, so we've now solved for theta 1. We can go back to our equations here for our robot. Okay, and if we look at equations 2 and 3 here, okay, we have our terms theta 3 and d2 here. So let's look at those equations. So that's elements 2, 4, and 3, 4 of our homogeneous transform. Let's write them out here. We have minus S1px plus C1py equals to minus C3g minus D2. And we have Pz is equal to minus S3g. So we can rearrange these. We'll bring the D2 over to the left-hand side. And now keep in mind, we already know theta 1, so we know that this side already. So we're going to bring D2 over to the left. So we're going to get minus S1px plus C1py plus D2 now is equal to minus C3g. And we have Pz is equal to minus S3g. So we'll call these equations 2a and 2b. All right, and if we look at them, so we got theta 3, cosine theta 3 here, and we have sine theta 3 here. So a trick in terms of solving this, if we want to try and isolate D2, we could probably square and add these two equations together and perhaps eliminate theta 3. So let's try that. So squaring and adding together equations 2a and 2b yields minus S1px plus C1py plus D2 all squared plus Pz squared is equal to C3 squared g squared plus S3 squared g squared. Let's rewrite that out. Leave the left-hand side as is. Group the g squared term. We know that cosine squared plus sine squared of an angle is equal to 1. Okay. Now we can just simply solve for D2 as we've eliminated theta 3 from this expression. So we're going to bring the Pz squared over to the other side. And we're going to take the square root. And keep in mind, both solutions, the positive and negative solution of the square root, are valid. All right, so you always have to use your plus or minus when you do the square root here. And now we can solve for D2. So D2 is simply going to be S1px minus C1py plus or minus the square root of g squared minus Pz squared. Again, now we should make a note, two solutions exist for D2. All right, so we saw we have two solutions for theta 1, and now we have two solutions for theta 2, or sorry, for D2. All right. We can now use these two equations here. Sorry, Justin, just delete that little bit there because I did a little scribble on the previous slide. I'm going to start here now. All right, so now we need to find theta 3. So we can go back to our two equations here, and we can see we have equations that in terms of C3 and S3. So let's use those two equations. So again, from elements 2, 4, and 3, 4, we had minus S1px plus C1py is equal to minus C3g minus D2. And we had pz is equal to minus S3g. We're going to solve for C3 here. So we have S1px minus C1py minus D2 all over g. And here we'll solve for S3. And we'll have minus pz over g. So now with S3 and C3 known, we know that theta 3 is simply going to be our a tan 2 of S3 C3, where S3 and C3 are defined above. All right, and you can see for theta 3 we have a single solution. So we've now found our complete inverse displacement. We found equations for theta 1, then D2, and then theta 3. So one thing to note, that there are actually up to 4 possible solutions for this inverse displacement solution for this main arm. Okay, so we had 2 solutions for theta 1, and we had 2 solutions for D2. So in terms of total number of solutions, you'd multiply this together, so there's 4 solutions. Because for each theta 1 solution, there's 2 possible D2 solutions. So we have to multiply this together. All right, and then once you choose the theta 1 and D2 solution, the theta 3 simply comes out from our equation here. But overall, there's 4 possible solutions for the inverse displacement problem.